Hello, everyone. Professor Reena Randir here. Our objective today is to understand the most important points in nuclear energy. You might have driven past a nuclear reactor and you would have seen these structures. And by the end of this lecture, you'll be able to make sense of what's going on in all of these structures that you see here. The main learning objectives is for us to understand what nuclear energy is. There's two kinds, nuclear fission and nuclear fusion. A very brief history of nuclear energy in terms of just making electricity, not the nuclear weapons. We learn how a nuclear reactor works. There's several kinds. We'll talk about the two most common ones, the advantages and the disadvantages of nuclear power and the future of nuclear power. Nuclear energy, it does not create greenhouse gases. So it's clean energy. And it is estimated that there's enough nuclear fuel for the next 100 to 200 years. So the thing is, we will run out of uranium, but it will take time. So it's not renewable. And this gas that you see coming out of these towers, it's not gas, it's steam. So it doesn't pollute the environment. So as the world is transitioning to clean energy, here is the potential, a very intense potential in nuclear energy. So here's a picture of an atom. So this is the Bohr's atomic model. All matter is made up of atoms. So when you study the atomic structure, the protons and the neutrons are held in the nucleus of the atom, and zooming around it would be the electrons, right? And all of them is held together by a lot of energy, bond energy. When you say nuclear energy, it is the energy that is trapped in the nucleus. So especially if it is an unstable atom, when you disturb the nucleus, it can give off energy. So this is what we are harvesting in nuclear energy. So when you say nuclear fission, it is breaking the nucleus to form smaller atoms, thereby creating energy in the form of heat. That heat can be used to heat up water, converting it to steam, and the steam can power turbines that will run a generator to make electricity. So nuclear energy is the energy trapped in the core of an atom. When you say fission, it is breaking an atom into smaller pieces to create energy. Fusion is when smaller nuclei can come together to make energy. Nuclear fusion is still in the R&D stage. It is not harvested yet, but it's good to know. There's potential there. One of the most common element that is used for creating nuclear energy is uranium. It is a heavy element. So, and it is unstable, especially one of its isotopes is very unstable. And then it can break easy and it can produce a lot of heat that can be harvested to make electricity. It is clean. There is a minimal carbon dioxide emissions, and there's enough uranium to supply the world for 100 to 200 years. Let's remind ourselves about what an isotope is. An isotope are atoms of an element with the same proton number in the nucleus, and they can differ in the neutron number. So if you take the isotopes of hydrogen, for example, protium has 1, that has no neutron. Deuterium has 1. Tritium has 2. All of them have the same number of electrons. So this will make them unstable. So the isotopes are able to sustain a fission reaction. So it is called that the element is fissile. So good examples are uranium-235 and plutonium-239. So here, these are the different isotopes in this table down here. You can see the isotopes of uranium. We have uranium-238, which is the most abundant form. Uranium-235 is about 1% of the uranium. This is the fissile form that will be used for nuclear energy. The other one is very rare, 234. So this uranium-235 is very unstable. And when the nuclear core is disturbed by a neutron, it will undergo fission, thereby creating a lot of energy. See, once the energy in the form of heat is made, that heat can be harvested to make electricity. The process is very similar as to how we make electricity from coal or any other fossil fuel. The technology part is the same. Here's a very clear picture of nuclear fission. Here is a heavy uranium atom. So when a neutron hits it, so there are many neutron startup sources here. So when a neutron hits a heavy uranium isotope, it can split to barium and krypton. So two lighter elements that will produce more neutrons, and they can go ahead and hit more uranium atoms. So every time the split happens, energy is released, immense amount of energy, tremendous amount of energy. And this reaction can go on. So it is called as a nuclear chain reaction. So this is what nuclear fission is. On the other hand, in nuclear fusion, two lighter elements will come together to form another element, thereby creating energy. And this is what happens in the sun and all the stars that are glowing. So in nuclear fusion, two light hydrogen nuclei will merge together to form another nuclei. So this type of making energy is in the R&D stage. It's not in operation now, but the potential is like beyond tremendous. If humans can master this technique, right, that is going on in the stars, there won't be a need for dirty fuels in the future. Here's another summary picture that shows the difference between fission and fusion. In fission, it is splitting heavy elements, thereby creating energy. Whereas in fusion, it is the opposite, fusing lighter elements. Elements that are lighter than iron, that means less than 26 protons in the periodic table, they can undergo fusion, releasing energy. More heavier than iron, they have the potential for fission when split. So this uranium splitting and the chain reaction, there's just tremendous amount of energy. So now this demands a requirement of a control or a control plate. So here, these control plates are for controlling the reaction. So what the control plate will do is it will absorb unwanted neutrons, thereby controlling the reaction. So here you can see uranium is usually mined, and then it is enriched. They're made into like a pellet form, and they are compacted in these rods. And then you can see between the rods is where you would see the control plates. The other one is called moderator. The word is missing. I'll fix it in the PowerPoint. So what moderators do, it will absorb the fast moving neutrons, and it is usually water, sometimes heavy water or graphite. They will slow down the neutrons, thereby keeping the whole system stable and safe. So there are two words that you have to know. Moderator will avoid an explosion in a nuclear reactor. by absorbing neutrons. A control plate will also absorb neutrons, and it will keep the reaction under control. So it becomes a stable chain reaction. Here's what a uranium core looks like. So it is mined throughout Western USA. In the world scenario, Kazakhstan, Australia, Namibia, Uzbekistan, and Canada are the top 5 uranium producers in the world. So the uranium will be mined, there'll be tunnels and they are mined, and then it is enriched. So that is the processing part. Then after it's enriched, it's made into fuel pellets that are compacted in rods. And that's what will be shipped to the nuclear reactors. Another thing to keep in mind is, see, uranium-235, once the chain reaction starts, there's a lot of radioactivity in it. So a lot of effort has to go into the proper disposal, because radioactivity can harm humans as well as the environment. So we have to devise a safe method of disposal of the nuclear waste. Another thing to keep in mind is the very high efficiency of nuclear energy. For example, the energy that is found in 1 pound of enriched uranium is comparable to 1 million gallons of gasoline. Isn't this something? Nuclear energy used to provide 17% of the energy in the world, but now it's down to 10% of the energy. So all the focus is going on like renewing what we once had. Nuclear plants are very efficient. It can run 24/7. Unlike solar and wind, we are not depending on the sun or the winds, right? So once it gets started, its efficiency is 93%, which is the most efficiency that you can ever see. So nuclear capacity factor by energy is 92.5%. Geothermal is 74, natural gas is 56, coal is only 40%. So this is very, very commendable. And nuclear energy is only supplying about 10% of the energy in the world now. So this graph is showing how since the 1970s, nuclear energy just took off. So you can see worldwide growth in almost all continents. You can see this. And who is leading the world in nuclear energy? It is USA for now. China is very close up, and followed by France. I love the statement, it's saying, if all our energy is coming from nuclear energy, we will reduce our carbon dioxide emissions by 98%. This is tremendous. When we are all trying to address climate change and climate action, this has a bright future, nuclear energy. Here are the nuclear reactors in USA. You can see how it's concentrated on the east coast of USA. We have US has about 94 operating nuclear reactors and 56 nuclear power plants in 28 states. With the new president, the bipartisan infrastructure by the infrastructure law, President Joe Biden has signed about $6 billion to have it going. And here in the bottom graph, it shows the nuclear electricity generation capacity up to 2020. So even though it is very intense, money intense, the government has allotted a lot of money to keep them going, which is promising. Globally, 10% of the electricity comes from nuclear, but there are certain countries that are very much ahead. Like if you take France, 70% of its electricity comes from nuclear. And here, if you take Sweden and these countries here, Ukraine, Belgium, Slovakia, they are all more than 50%. USA, it's less than 20%. So the potential for growth is immense. A very brief history of nuclear power in terms of creating electricity, okay, not in terms of creating nuclear weapons. So here in the turn of the century, Albert Einstein publishes his very famous, the miraculous 4 papers that describes energy is mc square. Energy is dependent on mass of the element, and c is the speed, right? So this kind of revolutionized thinking in the physics. So he gets a Nobel Prize. It's very commendable. So very soon in 1938, nuclear fission is discovered by German chemist. In 1942, Fermi demonstrated the nuclear chain reaction in Chicago. 1940s, the Manhattan Project, or the atom bomb, that devastated the world and ended World War II, started. In 1954, the world's first nuclear power station to make electricity operated in Soviet Union, Russia. And here's a picture of the largest nuclear power in Japan. Kashiwazaki Kariwa nuclear power plant. What are some of the main parts of a nuclear reactor? So like driving by, you would have seen these very complicated looking structures like a chimney or a dome. So because nuclear power comes from radioactive materials, it needs a very powerful concrete, very thick containment building. And it has where the fuel is going to be burnt, so shown in green here. It will have steam generators, steam pipes, and of course, it should have a turbine. Number 5 is the turbine. 6 is the generator for making the electricity, and also transformers. And then it is transferred to the electric grid. So the main goal here is we want to make the grid as carbon free as possible. So nuclear energy is vital for that. And because there's so much heat, we need a lot of water to cool it down. So water supply is required. So in a nuclear power plant, the chain reaction is started in the containment building, mostly using uranium or plutonium to start the fission reaction that will heat up the water that is circulated here to make steam that will run the turbine. The turbine will create electricity in the generator and transformed and then put in the grid. Here is a excellent picture that explains the different steps of a nuclear reactor. So the fuel, and here, this is where you can see the control rods, that will keep the whole chain reaction under control by capturing the excess neutrons. There are 2 main types. There are more types. One is the pressurized water reactor. There are 2 water loops. One is the primary water loop where the heat transfer will happen, here shown in purple. And there's also a secondary transfer loop where the steam will turn the turbine. In a pressurized water reactor, the heat generated by fission to heat the water is pressurized. So here, in order to avoid the boiling. The water was then circulated to a steam generator to produce steam that will drive the turbine to make electricity. Here is a very good animation of it. The second type is boiling water reactor, where heat generated by the fission will heat water to boil it, and then that will turn the steam will turn the turbine in order to make electricity. Both of the reactors that I just mentioned will allow the steam to be turned back, and the water is reused in this process. Of course, one of the things that's on top of everybody's mind, is the safety of nuclear energy. With the recent nuclear meltdown in Fukushima in Japan, right, which devastated the country, and Chernobyl. So these are like also the 3 Mile disaster. So all of this brings into our mind, how safe is nuclear energy? And here is the data from our world in data statistics. There's more deaths in coal, oil, and natural gas when you compare it with the nuclear energy. The problem with nuclear energy is that if there is an accident, the radioactivity can take hundreds of years to neutralize. So if you take death-wise, nuclear energy is very, very low, and it is considered to be safe if all the safety measures are taken into place. So what happens to the nuclear waste and how it is disposed? Sometimes, so it is packaged into these uh, little containers with radioactivity, depending on how radioactive it is, and it is disposed near the surface in these walls. But the most uh, accepted way is to store the radioactivity deep in geological formations, like deep into the earth, see 1,000 meters under. So they are, so that the radioactivity doesn't harm the environment or humans. So these are all very expensive endeavors. Sometimes they are even stored in water to cool it down, dissipate it, and then put in these concrete walls deep under the earth. So the main advantages of nuclear energy, of course, it's lower greenhouse gas emissions. And this is reason enough. It is very, very powerful. It is reliable. It is efficient. Once we have it running, the cost of operation is very low. We have supplies to last for 100 to 200 years. So it's not renewable. Easy transportation once the raw material is made. And 28 grams of uranium releases as much energy as 100 metric tons of coals. So it's highly efficient. The main disadvantage is the high initial cost of setup. Building a nuclear reactor runs in billions of dollars. Another thing is the nuclear waste problem, storing it, for hundreds of years until it becomes neutral. And then, of course, it's the risk of nuclear explosion. So because meltdowns has been in the news. So this is why the common people, they don't want this because it's very risky and long construction time. So there's both pros and cons. So what is the future of nuclear energy? It is kind of very uncertain, because even though, see here, you can see how it is nuclear reactors that used to supply 17% of the nuclear energy in the world is down to 10% now, because there are many that are closing soon. It's mainly because of the disasters that has happened in the recent years. So here you can see, if you see this blue, the turquoise blue, Germany is closing most of its reactors. Many have already been closed or being planned to being closed. So there are many closed downs the world over, but however, in China, you can see there is a 6% increase that is projected, with 70 new reactors being built. And here there's a lot of focus on STEM innovation. So here there is something called new scale design, which is pressurized water that will cool the core, with a reactor being immersed in a pool of water, thereby trying to minimize accidental meltdowns. So the future of nuclear energy is uncertain. There is a growth in some countries, and some countries are closing it down. But when it comes to the question of addressing climate change and reducing carbon dioxide emission, it has a tremendous potential. And I hope that was helpful.